Hello, my dear students of Benguet State University. Welcome to our online class. I am your teacher, Jan Lasea. Ladies and gentlemen, a blessed day to everyone. This is my second lecture on our subject, IT 121, Platform Technologies. In my previous lecture, we learned the concepts of computer architecture and computer organization, structures of computer, functions of computer, data processing machine, components of the CPU, and why study computer organization and architecture. Today, let us study languages, levels, and virtual machines. A digital computer is a machine that can solve problems for people by carrying out instructions given to it. The term digital is any electronic device that processes binary data made up of ones and zeros. Examples are digital camera, digital video recorder, digital TV, digital clock, smartphone, computer, to name but a few. A sequence of instructions describing how to perform a certain task is called a program or a software. The electronic circuits of each computer can recognize and directly execute a limited set of simple instructions into which all its programs must be converted before they can be executed. These basic instructions are rarely much more complicated than add two numbers, check a number to see if it is zero, copy a piece of data from one part of the computer's memory to another. Together, a computer's primitive instructions form a language in which it is possible for people to communicate with the computer. Such a language is called a machine language. To actually speak to an electronic machine, you need to send electrical signals. The easiest signals for machines to understand are on and off. So the machine alphabet is just two letters. Just as the 26 letters of the English alphabet do not limit how much can be written, the two letters of the computer alphabet do not limit what computers can do. The two symbols for these two letters are the numbers 0 and 1, and we commonly think of the machine language as numbers in base 2, or binary numbers. We refer to each 0 or 1 as binary digit, or bit. Computers are slaves to our commands. Hence, the name for an individual command is instruction. Instructions, which are just collection of bits that the computer understands, can be thought of as numbers. For example, the bits 100011001010 tell one computer to add two numbers. The people designing a new computer must decide what instruction to include in its machine language. Usually, they try to make the primitive instructions as simple as possible, consistent with the computer's intended use and performance requirements, in order to reduce the complexity and cost of the electronics needed. Because most machine languages are so simple, it is difficult and tedious for people to use them. Look at these machine language commands that are made up of 1 and 0. It is gibberish, or it does not make any sense. These machine language commands will display the letter A on the monitor screen. This simple observation has, over the course of time, led to a way of structuring computers as a series of abstractions, each abstraction building on the one below it. In this way, the complexity can be mastered and computer systems can be designed in a systematic organized way. There is a large gap between what is convenient for people and what is convenient for computers. People want to do X, but computers can only do Y. Convenient means programmers prefer writing computer instructions or codes in English rather than in machine language made up of ones and zeros because it is easy to understand. But the computer has limitation. The computer speaks only in machine language, binary ones and zeros, and it is permanent because the only way to represent if there is the present and absent of current or electricity that flows in the circuit is 1 for on switch and 0 for off switch. Question. Suppose we are inside a classroom holding a face-to-face class. A Chinese tourist visit our class. The Chinese cannot speak in English. What shall we do so that we can communicate to our visitor? Answer, we need to hire an interpreter who can translate English to Chinese and vice versa. So there is a language problem between human and computer. How do we solve this problem? Your guess is right. The problem can be attacked in two ways. Number one, design a new set of instructions that is more convenient for people to use than the set of built-in machine instructions. For example, programmers use a new language like the basic programming language. As example, suppose we want to clear the screen by writing the command clear. Since the computer speaks machine language, the basic command clear will be translated to its equivalent machine language made up of 1 and 0 or binary numbers. Therefore, programmers like us no longer write codes in binary numbers, ones and zeros. The basic language is language L1 and the machine language is language L0. The high-level English-like basic programming language is translated into a machine language so that the CPU can run and execute. The first programmers in the 1940s using ENIAC computer communicated to computers in binary numbers. But this was tedious that they quickly invented new notations that were closer to the way humans think. At first, these notations were translated to binary by hand or manual, but this process was still tiresome. Using the machine to help program the machine, the pioneers invented programs or softwares to translate from symbolic notation to binary. The first of these programs was named an assembler. This program translates a symbolic version of an instruction into the binary version. For example, the programmer would write add variable A, comma, variable B, and the assembler would translate this notation to 100110010101000. This instruction tells the computer to add the two numbers A and B. The name coined for this symbolic language is still used today, that I hope you will learn it in assembly language in your laboratory subject, is assembly language. Machine language is the native language of computers. These instructions are written in a series of ones and zeros that are directly understood by the computer. Assembler is a program or a software that translates assembly language instruction into machine language. An assembler translates the assembly language instructions before they can be understood and executed by the computer. Assembly language is a type of a low-level programming language in which mnemonic abbreviations represent machine operations and storage locations. It uses symbols or mnemonics to represent instructions instead of series of 1 and zeros. Here is an example of a assembly language made up of symbols or mnemonics. Translation is a method of executing a program written in language 1. Is first to replace its instruction in it by an equivalent sequence of instruction in language 0. The resulting program consists entirely of language 0 instructions or machine language. The computer then executes the new language 0 program instead of the old language 1 program. Example of translation are compiler and interpreter. Programmers today owe their productivity and their sanity to this observation. Programs that accept this more natural notation are called compilers, and the languages they compile are called high-level programming languages. They enable a programmer to write this high-level language expression A is equal to A plus B semicolon. The compiler would compile it into this assembly language statement, add variable A, variable B. The assembler would translate this statement into the binary instruction that tells the computer to add the two numbers A and B made up of 1 and 0, like 1 0 0 0 1 1 0 0 1 0 1 0 0 0 0. Interpreter means it is a software that reads the source code, translates its equivalent instruction into machine language, and the CPU runs or executes machine language equivalent in real time. Examples of interpreter are Quick Basic, Python, Ruby, PHP, JavaScript, GNU Octave, the language R, and MATLAB, to name but a few. On the other hand, compiler is a software that reads the source code, translates its instruction into machine language, and stores the machine language into an executable file. Some examples are C#, VB.NET, C++, Pascal, and Assembler, to name but a few. The basic language interpreter reads the basic command clear and translate into an equivalent machine language made up of binary numbers, ones and zeros, that the CPU runs or execute in real time. On the other hand, the compiler reads a high-level language command like print the letter A and translate first to assembly language for easy translation into machine language and stores into an executable file. The CPU runs or executes the executable file. Here is an example code written in Python that demonstrates interpreter. Let us compile, run, and test. The Python code will issue a command to the user to enter the first integer number. I will type 5. And then a second integer number to be input by the user. I will type 3. And the Python interpreter just translated the Python code into a machine language, and immediately the CPU ran the code, the machine language code, in real time. Here is an example code written in assembly language. Let us run and compile. The assembly language code asks the user to enter the first integer number, so I type 5. And then second integer number, I will type 3. The assembler translated the mnemonic symbols of assembly language into a machine language and stored into an executable file. And the CPU runs the executable file. And here is the executable file, prog.exe. If I run it, it runs our assembly code. The assembler compiler created the machine language equivalent of the mnemonic symbols and store it into a executable file. Whereas the interpreter Python does not create an executable file. If you want to run your program made in Python, you need to have a copy of this source code in order to run. Whereas a compiler like assembler, no need to have the source code because the machine language already translated and it is stored in this executable file and ready to run. I posted your second assignment in our Google Classroom. Please answer and accomplish it. That ends our topic for today. I hope you have learned in my class. Thank you for watching. Carry on until tomorrow. God bless us.